Welcome to this explainer. If you've ever wondered how scientists actually plan to physically hide our industrial footprint, well, you are in the exact right place. Today, I'm going to be your guide as we unpack a truly massive and frankly fascinating undertaking, the Department of Energy's 5th edition of the Carbon Storage Atlas. We're going to dig into the hard data, the subsurface maps, and the incredibly rigorous methodologies that are making carbon storage a reality.
So just like any high-level briefing, we've got a game plan. We're going to systematically cover 4 key areas today. 1. The carbon capture solution. 2. The geologic storage atlas. 3. Mapping capacity and uncertainty. And 4. Creating global safety standards. Let's jump right in.
Starting with Section 1, the carbon capture solution, defining the scale. We really need to establish a baseline here for exactly what we're trying to achieve when we talk about carbon management.
Now, before we can map our subsurface future, we have to actually define the process itself. Carbon capture and storage, or CCS for short, is essentially a giant interception strategy. It requires stepping in and physically separating carbon dioxide from the emissions of power plants or industrial processes right at the source, literally before those gases have a chance to hit the atmosphere. Once it's captured, that CO2 is transported and securely locked away deep inside the Earth in permanent geologic formations. It's just a massive logistical and engineering loop happening right beneath our feet.
And what's super interesting here is how the Department of Energy doesn't just put all its eggs in one basket. They investigate multiple pathways simultaneously, specifically looking at both pre-combustion and post-combustion tech. The goal of the program is completely neutral. It aims to let the United States keep benefiting from secure, affordable fossil fuel resources, but while drastically cutting down the associated CO2 emissions. It's all about adapting the infrastructure we already have, from natural gas combined cycle fleets to huge industrial facilities, so our economy stays competitive without throwing our environmental targets out the window.
Moving right along to Section 2, the geologic storage atlas, a modern treasure map. Because, well, once you capture millions of tons of carbon, it absolutely needs a permanent home. This brilliantly illustrates a concept that you could basically call reverse mining. Instead of digging into the earth to extract resources out, we are locating vast permeable saline formations far beneath the surface. The whole process involves injecting the captured CO2 downwards, safely trapping it beneath impermeable caprock. But at the exact same time, we're bringing treated brine, basically salt water, up to the surface. That extracted brine can then be treated at a facility and reused for things like electricity generation or treated water. It is a really elegant, balanced exchange of fluids deep within the Earth's crust.
Now, to understand why this storage is actually safe, I want to direct your attention to the critical depth line, which sits right at about 800 meters down. To put that into perspective, that is roughly the height of the world's tallest building pointing straight down into the dirt. Past that exact threshold, the immense pressure and temperature of the Earth force the carbon dioxide to undergo a literal physical transition. It changes from a buoyant gas into a dense, supercritical fluid. When that happens, its density skyrockets, meaning it takes up way less space and behaves much more like a liquid. And that is an absolute requirement if we want permanent, secure storage inside the microscopic pores of these deep rock formations.
But here's the catch. Because this safe storage relies entirely on these highly specific, permeable and porous rock volumes, we can't just treat the underground like it's some giant empty void. Which means there's absolutely no carbon capture without geological storage. These viable storage targets have to be hunted down, quantified and mapped out exactly like we would look for gold, oil, or any other valuable natural resource.
Which naturally brings us to Section 3, mapping capacity and uncertainty, the scientific challenge. We have to figure out how to confidently measure something miles beneath our feet across entire continents.
So how do we solve this? Well, the National Energy Technology Laboratory, or NETL, uses this genuinely ingenious spatial tool called the variable grid method. When you're assessing all these onshore and offshore reservoirs, from unmineable coal beds to organic-rich shales, you are dealing with mountains of data, and the confidence levels are all over the place. Think of it kind of like a digital photograph. Small grid cells, that means crisp data, high certainty, and a very tight range of uncertainty. Large grid cells, on the other hand, are like your blurry pixels. They represent high uncertainty where we probably need to do more sampling.
The really crucial takeaway here is that this method doesn't just give us a static, boring map of where rocks are. For decision makers, it actively offers a mathematically rigorous measure of risk. Whether they are looking at vector data, probabilistic models, or sample variance, this tool visualizes exact confidence levels before a single shovel hits the dirt. It totally customizes the spatial interpretations so industry leaders can get a crystal clear picture of exactly how solid the science is for any specific geographic region. And by continuously refining these methodologies and running empirical simulations across diverse reservoirs all over the US and Canada, the ultimate scientific goal of this program is highly specific. They are actively working to predict actual reliable storage capacity to within a plus or minus 30% accuracy margin. That right there is the gold standard required to actually give the industry the green light to go ahead and invest in multi-billion-dollar capture facilities.
All right, on to our final section, number 4, creating global safety standards, the rules of the subsurface. Finding the location and calculating the volume is really only half the battle.
To ensure complete safety and to actually encourage widespread global deployment of this tech, NETL researchers have developed an exhaustive library of best practices manuals. We're talking monitoring, verification, accounting, and site screening. And let's be clear, these are not just polite suggestions. They are the foundational blueprints for legal and regulatory frameworks all over the world. If a utility company or even an entire nation wants to start a storage project, these manuals define the exact uniform approaches required to do it securely.
Honestly, these manuals govern the entire life cycle of a project, the whole shebang. They dictate the criteria for initial site screening, how to run simulations, the mechanical requirements for building and closing the wells, and most importantly, long-term MVA. That stands for monitoring, verification, and accounting. Because at the end of the day, we have to be able to account for every single ton of CO2 that is safely sequestered underground for generations to come.
But hey, the science doesn't operate in a vacuum, right? These manuals even mandate strict protocols for public outreach and education. The Department of Energy completely gets that deploying these incredibly complex, clean technologies requires a lot more than just good engineering. If you're going to pump millions of tons of supercritical fluid below a region, the local community absolutely has to have total transparency and trust in the safety, the monitoring, and the science behind the whole process. So when you combine the ultra-precise mapping of emission sources with these highly regulated storage methods and best practices, the Carbon Storage Atlas basically transforms from a standard government document into a literal treasure map for modern carbon management. It hands decision-makers absolutely everything they need to physically mitigate emissions.
We've got the granular geologic data. We have the visual mapping tools to account for the uncertainty. And we have the rigorous operational rulebook to safely lock away our industrial footprint deep within the Earth. Which really just leaves us with one profound question to think about. Armed with this exact blueprint, do we actually have the operational discipline to execute this incredible engineering at a global scale and reverse our atmospheric footprint? Thank you so much for joining me for this explainer today. I really hope this deep dive gave you a fresh perspective on the very real mechanics of carbon storage.